quick survey. How many people here are using Git? Right. That's it. It's amazing how fast the adoption of Git has grown. I've never seen a sea change in technology this large at all. But Git is quite powerful, and there's a lot of low-level stuff you can do with it. And I think this is quite a popular talk, and I've done it a few times now. And I think a lot of people have hit that stage where it's like, oh yeah, I know what I'm doing. I'm going to do that. Oh shit, what the hell just happened? This talk is that talk. This is not a talk about this is how you use Git. This is how you get out of screwing up Git, which everyone does. It's a rite of passage. See, in the early days of talking about Git, we talked a lot about, it's a content addressable system, it's a content addressable file system, it's an acyclic graph, blah, blah, blah. But that's not a lot of use. So last year at Git Merge, the big Git conference in Paris that year, I saw Emma Jane Hodgson-Westby, great speaker, see if you can. And she teaches Git to people who really just want to get their job done. They don't want to hear about acyclic graphs. They don't want to hear about content addressable file systems or any of this stuff, rev specs, whatever. They want to just get their job done. So she teaches it from a much more intuitive, this is how you get your work done kind of way. The problem is, as you start to adopt Git, you tend to get into situations like this. This, by the way, is a recommended workflow. I shit you not. Don't do that. Okay, do the absolute bare minimum required. I get this question a lot. Just do the bare minimum you require in terms of branches and add more as you need them. Don't adopt something just because somebody told you on the internet. See, the problem is eventually you're going to hit this wall in Git where you're going to get into this tangled mess and you won't be able to get out of it. Probably you. But there'll be that one guy. Everyone knows that one person. Not necessarily a guy. Who whenever these things happen, you go, oh God, what the hell happened? And they go, oh yeah, type this. And then you'll get out of it. So presumably you'll see this XKCD. It's an instant classic. It had also the text as well. In there, in the README is that guy, the phone number of that person who knows how to get out of the trouble. He'll tell you what commands to use. Here's the thing. That guy doesn't actually know what those commands are. But he knows how Git works. Therefore, he can work out those commands must exist and work backwards from there. So it's great to start at the top. You definitely should start at a high level, understanding what git clone does and how you do a basic workflow. But at some point, you're going to hit this wall, and you need to understand Git from the bottom up as well to get out of trouble. And then you can be that person, the person that everyone comes to and says, I don't understand what's going on. You seem to have this magic understanding of Git. Can you help me out? Good for your job security. So without further ado, we're going to start with talk about Git, but we're going to go from the bottom up. We're going to start with the blob. The blob is one of the most fundamental data structures inside Git. There are really 3 types of them. Maybe 4. If you actually dig through the source code, there are others, but these are only ones of real interest. The blob is simply the contents of your file, or some metadata in certain cases. There are really 3 types of blob. The content, this is literally the content of your source files, your PNGs, whatever you stuck into Git when you've done a git add. There is a tree, which looks a little bit like a Unix file system or a directory listing. And there is a commit that can change over time. And that's pretty much it. That is Git in a nutshell right there, the fundamentals of it. But obviously that's a slight oversimplification, so let's actually go and poke around inside Git. So what I've done here is done git init, which, as I'm sure you all know, creates an empty repository. It does create some boilerplate in there. I've skipped past that, the hooks and stuff. Don't worry about those. That's at a much higher level. We're going to look inside the objects. So inside the .git objects directory, we have 2 other directories. So tree just does recursive lookup for your directories. So these are just 2 empty directories. That's all they are. So that's not very interesting. So let's add a file to it. So we're going to add a file into Git. We're going to do touch, which just creates an empty file, and then we're going to git add it. That puts it into the index and says, Git, I want you to track this. Don't commit it yet, just track it. We're going to track changes to this from now on. So what does it look like after that? Well, now we have an object, a blob. That is nothing more than the contents of that file, which in this case is nothing, zlib compressed. And you stick a header on it, literally the text blob, just so you can identify the difference between commits and so on. And then you zlib compress it, and you SHA-1 hash it. And that's it. Now, the important point there is, and this is what we're talking about with a content addressable file system, is anywhere in the known universe where you perform that action, an empty file will always give you that hash. Therefore, if I have multiple empty files in the file system, there will only ever be one of those, which raises a slightly higher, we're interested in how do you give it a name? Well, that comes a bit later. But first, let's do a quick commit. So we're going to do our first commit, committing this empty file into the tree. So now what we got? We actually have 3 hash files, 3 blobs. The first one is our blob, our empty file, same everywhere in the universe because it's the contents define what its hash is. We also have a tree and the commit. So these are all just stored as these zlib compressed and hashed objects. So if you perform these exact same actions anywhere, you'll end up with those same 3 objects. But now let's change something. We're going to add a comment to this text file. We add it, and now we have an entirely new blob because the content has changed, the hash has changed. This is the fundamental part of Git. It's every single, even a single bit change creates an entirely new type of file, or an entirely new object. Now, this is important, and it's not something you need to worry about right now, but I do talk about this. So this is why we have things like git LFS. If that file was a 50 meg image and I change 1 pixel of it, I've now got 2 50 meg images. So this is a bit of a problem. That's a higher level one. I do another talk about git LFS. But these are the fundamental objects. You've got your commits, your trees, and your blobs, which are just the contents of files. And let's have another look and see how this fits in with commits over time. So here we have master, and we'll talk about exactly what master means in a bit. And it points to a particular hash, which also may point at other hashes. Now, those hashes are normally a commit. So commits can point at other commits, as in their parents. So this is what we talk about when we're doing sort of commits and changes over time. But let's have a look. So I like poking around inside things. So here's one fun thing to do is look at getCAD file. That will take any object in that tree and print it out in a manner appropriate to what you're looking at. So it'll format a tree or a commit in a meaningful way. But this is what it looks like. And that's literally what a commit is. It's essentially a text file with some metadata in it. And we've got our standard metadata here. We've got our committer and the author and your commit message, standard stuff you'd expect to see in there. We have the parent, which says this is the commit that came before me and how we define changes over time. But also there is this object tree. And this tree points at that other special object I mentioned before. So what does a tree look like? Well, we can do a cat file again. Very, very easy to do. I recommend going and playing around with this. You learn a lot poking around. What does that look like? Again, it's essentially a text file. And it contains some metadata about the directory that we've checked in. So, for instance, it contains a file mode. When this file is when you check this out, when you pull this out and turn it into a working file, this is the mode it should have. This is the type of object it is, just really for convenience, and the SHA-1 of it. So this is how we assign metadata to those objects. Those objects don't inherently have names or modes or anything. They only have the content. We assign the names at the tree level. Because that's important, because if we have 2 different files that are both the same, then we'll only have a single object. So we want to give them different names. Well, we do that at the tree. We don't do that at the object level. So here's how we assign the names to them. So this is all very nice, but of course one of the nice things about the trees is they can be recursive. Trees can point to other trees. It gives you a deep directory structure. So if you actually look at this, it looks an awful lot like a Unix file system, which is not entirely surprising given it was originally written by a guy who's a Unix and file systems guy. And this, of course, can change over time. So each commit points to a previous commit, apart from the first one, of course, and that defines our history. And each one points at a tree, potentially a different tree. If you change any of the file names, if you change any of the objects, that will have changed the hashes of the trees, of the commits, etc., etc. So you end up with this history over time. But because it is a content addressable file system, in practice, this history will share a lot of the same objects. Because if it hasn't changed, its hash hasn't changed, so we will reuse that file again, the object. So that is a very, very low-level look at the core data structures of Git. Now I'm going to jump one level up here, not very high level, you'll see, to talk a little bit about refs, branches, and tags. Helen?
Just a question.
Yeah.
Before going on, but what if there's an hash collision?
Statistically, very, very, very low. SHA-1 was not the best choice for this. SHA-1 is now known to have some hash collisions, but collisions, when you talk about SHA-1, those aren't those short numbers. The number is actually like that long. So the actual chances of collision are exceedingly low. There have been some theoretical attacks on that. I think Git should probably think about moving forward to SHA-256. Git LFS has moved to SHA-256. LFS is our large file system add-on to Git. But yes, it is an interesting question, but generally speaking, it's more of a theoretical problem than an actual one. So, refs, branches, and tags. So we've talked so far about hashes. The problem is hashes aren't very useful in practice. I can't go to you, can you check out FCFA1147? That's not a great way to work. You want to say, I want you to check out the last release, release 23. You want some way of naming these hashes, naming these points in history. And that is what refs are for. So the lowest level of that naming system is a ref. A ref is literally just a pointer to an object. That is all it is. It can be pointed to any object, but generally speaking, you're going to want, sorry, before a bit there. But generally speaking, you're going to want to point at a commit. Commit is generally what you're working with at the in terms of timelines, but it can theoretically point at any object in the tree, and I will play with that a little bit later on. A branch, on the other hand, is a divergence from a common point, but it is basically a ref. Branching is very, very cheap in Git because it essentially is a no-op. It only becomes an operation when you try and merge back. By having a separate point of divergence, you can carry on a different stream of development in parallel, but all it is having a different name for the latest commit. And at some point, those two commits will go back in the past to being one stream of development. A tag is simply a special type of ref that says, I am actually a static point in time. Usually speaking, the simplest form, the tag is just a pointer to a commit, normally a significant commit, a release point, a known good working version, etc., etc. There are special tags that you can add additional metadata to, and even sign, which makes them immutable effectively. But at its basic level, a tag is just a pointer to a hash. So in many ways, the references are like variable names in Java or similar languages. It points to a memory address, and it gives it a name that you can refer to. Under the hood, where it's working with real objects in Git, under the hood, it will be using real hashes, but the references are just a way of giving human readable names to it. Now, what do these look like? So let's play around with our little tree again, our little repository. and we're going to create a branch and a tag. And then we're going to look inside the git refs directory. And as you can see, we now have 3 files in there. One is the master, traditionally the default branch, a branch, and the tag. But if we actually look at that, all that is literally, I'm not even doing that getCAD file. That's literally just the contents of those ref files. They are literally just the hash. That's why branching is so fast, and tagging and so on is so fast in Git, because it's literally you're writing a handful of bytes to a file. Now, that is the most basic stuff. I'm now going to talk a little bit about some of the operations you can perform. And generally, you're often performing operations either on creating and gluing together these different types of objects, or you're working on increasingly, if you're messing around, trying to branch, trying to rebase, things like that, you're generally operating with the references. So let's have a look at one of the most fun ones to do, is a reset. How many people here have played with reset in Git? How many people fucked it up? Yeah, the ones who didn't put their hands up are lying, all right? Everyone, this is a rite of passage. You will do this, you will screw it up. All it does is, at its simplest level, it will just move a particular reference. Now, there's a little bit more to it than that, as in there are flags which define what happens to the working tree after you do that. But 9 times out of 10, you're going to do hard, because you think, oh yeah, I know what I'm doing. I'll git reset hard, boom, what the hell happened? Okay, and you probably went, oh, that is gone forever now. No, it's not. Because we are about to learn the most useful thing you will learn about Git. If you take nothing else away from me rambling here, you'll take away this, the ref log. Every time you manipulate a reference, that means creating a branch, merging a branch, pretty much anything you do in Git modifies references in some way. It gets entered into a ref log. It's the history. It's like your bash history. It's like your web history. It's where you've been and how you got from there to here. And that gives us a tool that allows us to get out of trouble. Because when you move that reference, you just changed a handful of bytes in a file. That has nothing to do with the content of those previous commits. They're still knocking around. So we can get out of that. So we will come back to that in a bit and show you how you can use the ref log to get out of trouble. And you will probably use that a lot from now on. But first I want to address a little thing I mentioned there. Git doesn't delete objects by default. On your local directory, it will not delete anything, at least not straight away. Not just because you did a commit, not just because you reset it. It generally won't do anything straight away to those objects, which means those objects are going to build up over time. And as pointed out, they're not super efficient. And that's not normally a problem because disk space is cheap. But once you get to chucking things over the wire and over the network, that's not a very efficient way to work. If you change one character in a file, you get the 2 copies of the file, and you're going to have to send both copies over the wire, and you're going to get both copies sitting on your disk. So we have the ability to keep things clean. Now, Git will do a certain amount of cleaning up for you only after a certain amount of time. But we have something called getGC. getGC is, if you know anything about Java or any of the other garbage collected languages, which is almost all of them nowadays, you'll know that this means garbage collection. What Git will do is basically looks an awful lot like how garbage collection works in pretty much any language. Is it goes through all the objects and says, can all of these be reached from somewhere? Do all of these have a name? If not, if they don't have a name or are not reachable via something else, then they cannot be referenced anymore, therefore they are dead. And it will go through and clean out any of them. Now, it doesn't do that very often. It will do it before you do a push or a pull. And you can do it manually, but even then it won't delete things for a while. But let's look at this again. So what we've done, we did a git reset. We decided we messed up that last commit. We're going to move it back and try it again. Now, if I force the situation, getGC prune all means just normally there's safety checks. You get about 2 weeks grace period before it will clean up any dead objects, just in case. So even if you do this normally, you can go back to the ref log and recover as long as you haven't waited 2 weeks. But here I've forced the issue by using prune equals all to show you, and it goes through and deletes that object. It also does something else, and I don't want to get too far into this because it's not super important, but if you are going to play around looking inside the Git repository, you should understand a little bit of this. I mentioned that throwing all these objects around over the wire on the network in particular isn't super efficient because you've got all these objects and there's lots and lots of duplication. Well, what happens when you GC is it also converts them into a different type of object store called a pack file. A pack file, after the GC, it looks like this. There's only 2 files. All the objects are contained inside that .pack file. What this is very esoteric. If you want to get an idea of how smart Linus Torvalds is, inside the Git repository is a documentation and a pack file, text file. And it's basically Linus Torvalds explaining how he came up with the pack file. And it really is just an email he sent to somebody saying, oh, by the way, this is how this works. Have fun. I'm out. And it's very esoteric. The entire thing is designed to get very, very good caching abilities and very, very good hit rates in terms of sectors on spinning disks. We're talking about a hardcore operating systems guy here. But if you ever worked with databases, this is going to look kind of familiar to you because it has 2 files, not 1. It has a pack file, which is the data, and an index that describes where in that file does your indexes, where are your objects, how you find them, and how do you get them back out again. So this looks an awful lot like the on-disk representation of any basic database. However, that is not super important because none of this actually changes the Git model internally. You don't need to think about pack files unless you're dealing with implementations. You do need to worry about them if you're going to be writing Git yourself, and if you want to, I recommend doing it. It's fun. It's a fun way to learn about Git. It's very, very simple, as I've pointed out. But this is just something to be aware of, but not super important. So having talked about pack files, ignore them from now on. But let's jump up another layer up the stack to the much harder thing. So I've shown you how easy it is to branch. You literally just create another tag, and then you work with that tag rather than your master tag. Well, that's great, but unless you're completely rewriting your application, at some point you're probably going to want to merge back in. How do you do that? Well, this is an esoteric subject in and of itself. But at a conceptual level, a merge is actually just a special commit, one that joins 2 pieces of history. Now, how that merge commit becomes is basically what happens is when you've branched off these 2 competing or complementary streams of development, you bring them back together. Git has to resolve any differences. Now, that's what the merge commit is. It's all the changes necessary to merge, to resolve all the differences between the 2. This means that merge commits are also special in another way, in that they have 2 parents. Now, there's actually no reason why you can't have more than that. There is something called an octopus commit, where you can actually take multiple streams of development and just merge them all together in one go. But unless you know what you're doing, I don't recommend doing that. It'll get messy very quickly indeed. So what Git does is applies a algorithm, and these algorithms are pluggable on how to resolve any differences between the 2 streams of development, and then does that merge. Except for in one particular case. Imagine if you have a master branch and you're working away and you go, oh, I'll do the right thing, I will branch off, make a bunch of changes there, and then do a merge. Meanwhile, no change has occurred back on the original master branch. What does the merge commit contain? It actually contains nothing, because there's no differences to resolve. So this is what a fast-forward merge is, if you've heard of that. A fast-forward merge is just a way of basically doing a null merge. All you do, you've got your master branch, you've created your separate branch, you make your changes and you do a merge. All it does is literally move the result, or basically make the two tags the same. You just move it forward. This is what Git does by default in this situation. Now, that can be a problem because sometimes this is one of the few cases where it's literally going to destroy information without you asking it, because you will no longer know that a branch occurred there. Now, some people like that. Some people like a clean history, singular and linear. But a lot of people like to keep the true history, and there's often information embedded in that history. For instance, if you've got a JIRA ticket, you may have named the branch after that JIRA ticket, and then you would like to keep that information around. So there is a special command flag to merge called noff that will not do a fast-forward merge and instead create a dummy merge commit that contains nothing other than the text file that says, I'm a merge commit. But it will not contain any changes because there was no conflict to be resolved. I mentioned that merge strategies and different algorithms available for merging. Now, I would have liked to go into this a bit more, but it is a very big topic in and of itself. But suffice to say, traditionally, when you've done a merge, or in most version control systems, it's used resolve. But in Git, it uses something called recursive. Recursive is something that was introduced with the Linux kernel tree, and it's been battle tested there, and it gives the lowest level of issues with a merge, even under very complex circumstances. You understand they've used it in the Linux kernel tree. You understand that it has been very well tested. What it will do is basically go back through the history, find any common points, and the way we've done cross merges, it will actually create dummy merges and then incrementally, recursively walk back up the tree doing merges as it goes. Very complex piece of technology. I used to include it in this talk, but it's a bit much itself. But there are others as well. There are things like Octopus that will take many, many branches and merge them all together. Unless you're 100% certain there is no overlapping changes, don't do that. We do use it internally at Atlassian for our blogging system, so that on our staging server, everyone's working on their own branches with their different blog posts, and we just pull them all together into one version on the staging server, so rather than everyone stomping all over each other when they push to the staging server. But it's also pluggable. So, for instance, if you have binary files in some proprietary format your company uses, you can just add your own resolver that will actually create the merging of binary files, things like that. But interesting, but not super important right now. We're talking about getting out of trouble, not getting ourselves into it. So let's look at one of our favorite ways of getting into trouble. Rebase. How many people here have tried to rebase? How many people fucked it up? Right. And again, the ones without their hands up are lying. So what a rebase is actually replaying history. So I have a branch, and I decide I'm not one of those people who likes a nice, clean tree. I don't want any merge commits in my tree. I want it to look clean. Perhaps I'm a contractor working for a company, and if they see any merges or anything like that, they get upset and they say, what were you doing? This is a question I get a lot. You would be surprised. Some people are quite funny about that. So they want a nice, clean tree. It's up to you. Git allows you to do whatever you want to do. So you do a rebase. Well, what does rebase do? Rebase basically makes it look like the branch never happened. Well, rebase can do a lot of things, but this is what it's used for 9 times out of 10. It replays history. So what we do is take each of the commits and effectively merge it onto the end of the or whatever target, which is normally master. And that gives us a clean history. Now, I don't go too much into this here, but if you think about this, you're replaying history. Replaying history is a great time to change history. So some of the things you can do with rebase, for instance, is say, I don't want there to be multiple commits. I want you to merge all these commits together as you move them across. Or I want to join two commits together, split commits up, change commit messages, whatever. It's a great time to change history if you do need to do that. But at its simplest level, Git rebase is nothing more than playing a piece of history, a set of commits, back in a different place, which is handy at times. But I promised you to show you how to get out of trouble. Did anyone recognize this, by the way? No? So this is original Prince of Persia, Sands of Time advert in Australia. I think I'm not the only person who remembers this. But it's quite cool. So anyway, I'm going to run through quite quickly how we're going to get out of trouble using some of the things we've learned today. So we've done our reset hard. We've established that it is very, very easy to get wrong. So we've done our reset hard. Uh-oh, how do we get out of this? Well, we know we have the pieces here. We know reset just moves refs around. And we know that we have something called the ref log. So we know where we were before we did that ill-advised reset, when we have the hash in question. So how do we get out of it? We just do exactly what we just did again. But this time, we say, we give it our piece of history. We can reset and make it look like it never happened. So that's a simple one. This is why I say, if you take away just the ref log from this talk, I've done well. The ref log is your friend. Another fun one is you do a rebase and you broke the build. I did this once, so it was massive. Complete pain. How do you get out of that without, basically just having to go back and, try and recreate everything again? Well, there's a couple of little tricks here. I'm going to show you two tricks. One is kind of obvious. We can rewind. Because we have the ref log and we have reset, we can just reset back to the place we were in before. And here's another fun one. If you do rebase a lot, rebase exec is very, very useful indeed. So rebase exec, because we're replaying history, we can change history, or we can operate on history. What rebase exec does, every time it does one step of that replay, it will run a command straight away afterwards. The most useful one, obviously, being test. It will then stop the rebase if the tests fail. Very, very useful indeed. But there is actually another fun way to do this. If you don't want to do that replay, it's something called bisect. This is used a lot in the Linux kernel world. This is really, really useful. What you do is you say, I know that there is a place where it was good. I also know there's a place where it's broken. What happened along the way in between? At what point did the breakage enter? And you can literally go, git bisect. I know this is where it's good. And then for each commit, you can basically, it will jump back to a midway point in history, and you can mark it as good or bad. Or you could even use, again, if you have your tests, you can use your unit test to be run for you, and Git will do this automatically and stop at the point where the breakage was introduced. It'll basically manually narrow down. So, very, very useful. Git bisect used a lot, particularly in the hardware world, where breakages often get found out much later because you can't unit test often. That's why it's used in the Linux kernel world so much. There'll be a regression that only occurs on Asus laptops from 2009 or something like that. And it probably only found that out like 6 months after the change was introduced. But talk a bit about how it works under the hood. Can we use this ourselves? Any toys we can do with this? Any little games? Well, why not? So the last thing, I'm going to show you powers of invisibility in Git. So I'm going to show you how to hide files inside Git repositories. So here you've got your standard Git repository, not very interesting. I want to hide a piece of data in it with unless you know or go digging around inside, you'll never know that it's there. Because this is Git, it's all just objects. We can manipulate those, we can manipulate refs. So how do we do this? Well, we can go, there's git hash object. Knowing what I know about Git, I know there must be a command in there somewhere to create these objects on the fly. And the answer is, yes, it is. So it's called hash object. And I can say, it'll by default, it will just give you the hash an object would create if you added it to the tree. with a minus W, it will actually enter it into the tree. That's great. So that's really how simple it is. We take a text file, we put it in there, and we have the hash, and we can refer to that hash. But it's not going to last. Why? Yeah. It'll be garbage collected at some point, normally after 2 weeks. But we know something else. We know that if it's got a reference to it, this won't happen. So we can create a reference. So we're just going to create a tag. We give it the name hidden, and we tell it, create a tag called hidden, pointing at that particular hash. And now it is safe. How do we get it out? Well, we already kind of seen this. I showed you this fairly right at the start, basically. We can just go cat file hidden. That will look up the tag, look up the reference, find the object, and spit it out onto the command line. And the answer is what that file is a old family recipe for poutine, which is sort of Irish vodka. It's illegal pretty much everywhere. My family has a questionable history. Now, this seems kind of interesting, but not very useful, except that it's actually used inside the Git tree itself. Junio, the Git maintainer, put his GPG public key inside there, but not part of the standard repository, and it just sort of floats there inside the Git repository with a tag attached to it and nothing else. Caused merry hell, because when the Bitbucket guys were implementing Git, the first thing they did was try to import Git itself into their Git repository, their prototype Git implementation in Bitbucket. And it kept blowing up, and they couldn't work out why. It took them ages to work out that they had all these floating objects that they're not part of the common history. But there are other uses for this as well. GitHub used to use it to manage Git pages. I think they may have changed that. I don't think it worked out very well. But because if you can do this, why can't you create completely separate streams of information inside a repository? You can literally jump between completely unrelated code bases. So what they did was just stuff all your GitHub pages into a completely separate repository inside the same repository. So a completely separate stream of commits. I don't think that worked out very well for them. That's one why Atlassian didn't do that. We have third-party systems for that. But there are things you can do. If you understand Git, you can go at a low level and manipulate it much more. But with that, I'm pretty much out of time. I've got a few minutes for questions. 3 minutes. But just to remind you, this is pretty much the entirety of Git at its conceptual level. You have blobs, trees, and commits, and they can all point to each other, and they can point backwards through time as they change. But that is essentially all you need to know about Git at its core. There are a few things we've skipped over, of course, but at its core, that is the conceptual model of Git. It is very, very simple indeed. And once you understand it, life becomes a lot easier. So with that, I think we've probably got I recommend, by the way, going back to your places of work and going in and actually directly manipulating your Git repository. If anyone asks you, just say, don't worry, Steve Smith told me it was fine to do this. Don't worry about it at all. So with that, any questions? Thank you.